Alright, so we're going to talk about angular momentum. So this is our last major topic. We're going to talk also a little later about how to use rotational energy and angular momentum kind of to analyze orbits, which is also this unit. But really, since that's just applications at that point, this is really what we're looking for here as angular momentum being our last major rotation topic. So before we talk about angular momentum, let's talk a little bit about linear momentum. So when we originally learned about linear momentum, we started off with Newton's second law, and we said that net force is equal to mass times acceleration. And we talked about the fact that linear momentum is actually really difficult to describe because it's a mathematical construct. So what we did is we said, okay, well, we know that objects that are moving and have mass are going to have momentum, and we know that bigger objects have the tendency to keep moving longer. That's kind of like inertia. But that in terms of inertia, and a big object at rest and a big object moving at some speed have the same inertia, but they will have different momentums. So momentum also has this speed aspect to it, this velocity aspect. So we're like, well, how do we get velocity into this conversation? Well, what we said is like, oh, well, our acceleration is change in velocity over change in time. So our net force was equal to m times the change of velocity over the change in time. And then we said basically that if I do m delta v, that's going to be like m times v2 minus v1 over our change in time, which is going to be the same thing as mv2 minus mv1 over change in time. And that basically this construct right here of m times v we defined as momentum. So then this gives us P2 minus P1 over delta T, which gives us the delta P over delta T. So we said that our net force was equal to the change in momentum over the change in time. And then we also define, say, the net force times the change in time, which is equal to the change in momentum. We define this as impulse, and we define this as our change in momentum. So that applying a force over time changes the momentum of an object. So that was linear momentum. So if we have an object that is going rotation, say consider a point mass going at some speed around the circle, that if there is a net torque, then there's going to be some change in angular speed, so that it can be going at one speed here, and then maybe at some other position here it's going at a larger linear speed, and therefore a larger angular speed. That there had to have been a net torque to make that change. So kind of going through that same process, we have this net torque equation for I alpha, which is Newton's second law for rotation. So when we started with linear momentum, we started with Newton's second law for linear motion. So if I replace that alpha as having a change in omega over the change in time, I can kind of go through this same process. And I have I times change in omega. If I'm assuming that I is actually constant through this, then I can say that I times omega 2 minus omega 1. And then my I omega 2 minus my I omega 1. Oh, I forgot my change in time there. Over the change in time. Well, this product here, I omega, we can then define as angular momentum. And we actually define angular momentum with the capital letter L. Okay, so that is our angular momentum, this capital L. So I can call this L2 minus L1 over delta T, which is delta L over delta T. So then I get my net torque is equal to the change in angular momentum over the change in time. So my net torque times my change in time is equal to my change in angular momentum. So there we have, this is Newton's second law for rotation in terms of momentum, angular momentum. So we define essentially angular impulse is equal to the change in angular momentum. If you have a larger rotational inertia, then that means you're going to have more angular momentum. If I have more rotational inertia, you're going to have a tendency to keep on doing what you're doing. So like a hoop rolling on a horizontal surface with some speed is going to be able to continue rolling further than, say, a solid disc with the same mass and radius, because the hoop would have a larger rotational inertia, so it's going to continue going further. Also, objects that have a higher angular speed are going to have more angular momentum. It's going to take them a lot longer to stop when the same force is applied on something that is moving at a slower speed, or same torque, I guess. This idea of angular impulse, very similar to our idea of regular impulse, which is force times change in time, except for this time our force actually has to be exerting a torque. But basically, the larger the torque you apply over a longer period of time, the bigger the change in angular momentum is going to be. So I think that kind of makes sense. Realize that you can then do like graphs of torque versus time, and then the area under the curve. Your area here is going to be equal to the change in angular momentum. Kind of like if you did a force time graph, the area under the curve is change in angular momentum or impulse. All right, so if we take a look at a point mass here, we know that this point mass is moving at some sort of linear speed that's tangent to the circle, and that it has a mass. It's located at a radius r. So if I was to try and find the angular momentum of this point mass, a point mass would have a rotational inertia mr squared, and its angular speed would be based on v equals r omega, so omega is going to equal v over r. So you're going to get v over r here. So I'm going to get an r canceling out, and I get that my angular momentum is equal to mr times v. So one thing you have to be careful of is this v does need to be perpendicular to r, or you can do r perpendicular to v. There are some cases when you're on grids where this is actually an easier calculation. So what's really weird and wonky about this is that this r is relative to some predefined axis of rotation. But if I remove this circle and I just have this point mass right here moving with some sort of m times v in a straight line, and there's no circle, there's no omega, like there is no rotation, this guy is moving in a straight line, but I define this position as my axis of rotation. Even if there is no rotation, I have an angular momentum. So I can actually calculate the angular momentum of this. And that angular momentum, if I rearrange this and make it r, is going to be mv perpendicular, or r perpendicular times mv. This mv is linear momentum. So I get L is equal to r times p perpendicular, which is equal to r perpendicular times p. So basically, momentum perpendicular to the lever arm, the moment arm essentially, and then, or I could find the momentum and find the component of r that is perpendicular to the momentum. So that would be, for example, if this thing was moving in this direction, and I wanted to find the r that's like component of the r that's actually perpendicular to this vector, I could do either one of those. So gets a little wonky because this does not actually require rotation. So you'll see these weird angular momentum problems where they're going to give you like some sort of grid. These often happen on grids. And they'll give you, I think there's one on your homework, they'll give you like a point mass going here. So this is like M1 and V1, and then you've got over here maybe one going like this way, and you got M2 and you got V2, or maybe they're all equal mass particles. And then you got one over here going, I don't know, like that. So M3, V3, and they'll be like, okay, rank their angular momentums. And then you're like, hey, but they're going in straight lines. I'm like, yeah, they're going in straight lines. These are not rotating. But they'll say, okay, rank their angular momentum about the origin. So basically what this equation is telling us to do is it's telling us that, okay, for each of these points, I need to find r. So I'd have an r for each of these. R is technically a vector. It matters more in physics. See that it's vector, that's why you have this perpendicular component, because you do vector addition here. And then what I do is I take a look at either one of these. So the first thing I notice is that in order to have angular momentum, I have to have at least some component of the momentum perpendicular to the lever arm or vice versa. And that's because in order to have a change in angular momentum, you have to have a torque. So therefore, you can't really have angular momentum if it's going parallel, because you're never going to have it won't change as you get further away and so forth. So this guy here actually has an angular momentum equal to 0. And then if you were looking, say, at this one is, I drew a kind of perpendicular. So this one's angular momentum would be pretty easy to find, because it's just going to be, L3 is going to be, let's see, R3, M3, V3. Because it's perpendicular. So this actually has, if these all maybe have the same mass, and maybe they're all at the same R or something like that, then this one is going to have the largest angular momentum, because it's actually moving tangent to the radius at that instant in time. Now, at the next instant in time, it's going to move in a straight line, and its angle will have changed, because when it's here at this next position, so maybe it's over here, well, it's now at a angle, so we have an angle that is not 90 degrees. So its momentum will have decreased in terms of the angle between them. So you'd have to find like either one of the components that's perpendicular. So you'd have to maybe find the component of the velocity that's perpendicular. So you can see that that's going to be smaller, but you've also increased your radius. So whether or not this angular momentum has increased is going to have to depend kind of both on the angle and kind of the radius at that point. You have to calculate that out. Now, this one, and this is kind of one of those ones where I said it's actually easier in some cases to do this, especially when you're on a coordinate system, because if I found V perpendicular would be here. But I'd have to like know what angle this was in order to do that. But I can easily find R perpendicular, because it'll be on the grid. So R perpendicular would be this vector here, and then I can just do L2 is going to be R perpendicular times M2 V2, and R perpendicular would just be whatever this x coordinate is for this particular situation. So you can do these linear type things so that you have kind of angular momentum for objects that are moving linearly. And it's just based on the linear momentum times r, which actually follows along with everything else that we've done with rotation, whereas our rotational quantities, like force and torque, are kind of equivalents, because linear forces cause change in linear acceleration, linear velocities. Torque causes a change in angular velocities. You have an angular acceleration associated with that. And to get between force and torque, all you do is multiply by the lever arm r. And that's the same idea here, where you just have to take your linear quantity and multiply by r. And just kind of like in both cases, you just have to make sure that your torques, your angular momentums, that they're based on those perpendicular relationships. All right, so let's take a look at the units of angular momentum. If we take a look, say, at this definition right here, the units of rotational inertia are kilogram meter squared, because it's mass times radius squared. Your units of angular velocity would be radians per second, but the radians are a placeholder unit, so when you do kilogram meter squared times radians per second, you get kilograms meter squared per second. This also works if you use this definition, because you would have meters for r, and then linear momentum is kilogram meter per second, which also gives you kilogram meter squared per second. The one last thing I want to talk about today is the direction. Because actually angular momentum is a vector. So angular momentum will always point in the direction of the angular velocity, kind of like linear momentum always points in the direction of the linear velocity. So for example, if I had an object here that is rotating and I wanted to figure out what direction the angular momentum was pointing, I can use my right hand rules. So remember to use the right hand rule to find the direction of, say, your angular velocity. If something is rotating, say, in the counterclockwise direction, if this is my axis of rotation, I curl my fingers in the direction that it's rotating, and where my thumb points is the direction of the angular momentum. So in this case, my angular momentum vector is pointing up to the top of the page, which is also the same direction as where the angular velocity is pointing. If this thing was rotating in the opposite direction, oh, that's not the opposite direction. If it was rotating in the opposite direction, then I would put my fingers going the opposite direction, the clockwise direction in this case, and then you can see that as I rotate my fingers around, my thumb would point down the page. So my angular momentum in this case is either going to point up the page or down the page. So the vector itself is actually perpendicular to the rotation itself. If I was looking at a point mass situation, so let's bring back those coordinate axes, and I had a point here that was maybe moving with some velocity up the page, what I'd have to do is I'd have to consider where R is. And R, I would assume if that's my axis of rotation, points in that direction, and that if I were to point my fingers in the direction of R, and I was to rotate my palm in the direction here, that actually I would end up with my angular momentum actually pointing up out of the page in that case, because the angular velocity associated with this motion would be a clockwise, counterclockwise angular velocity, which would be the same thing as kind of out of the page with that. So this one is a little trickier just because of R is technically a vector. This is actually a cross product, a vector cross product. For those of you in higher calculus, you might have seen cross product before. That's why it's a little wonky. So let's say I had like a point over here that was moving with some sort of velocity and mass. Go through the same process just to make sure we get it. If I were to draw the lever arm starting at the axis of rotation, there's R. Point my fingers in the direction of R, rotate my palm in the direction of the velocity, and then curl my fingers. In this case, I would end up with an angular momentum that would be into the page, because that would have an associated angular velocity that would actually represent more of a clockwise motion. So even though these objects would not actually be rotating, they do have angular momentum. So like these are really hard kind of to grasp for a lot of people. I think just the situations of nice pure rotation are a lot easier for most people to handle. So please make sure to contact me if you have any questions.